In science, numbers and measurements are important. Although some calculations may not be highly complex, simple mistakes can be made that have drastic consequences. Simple and routine calculations can be so simple and routine they are not given the full attention they deserve. As a result, mistakes are made. Unit errors in the medical field demonstrate how simple mistakes can have complex and drastic consequences. For example, dosage conversions between English units, a base of 12, and metric units, a base of 10, are measurements that are not complex, but errors do occur with some frequency. Other common errors are labels that are misread or miswritten. Database entries are also sources of human error. Details are important. Examples of calculation mistakes are as follows. In a 1999 case, the Institute of Safe Medication Practices reported that a surgical resident read a patient's prescription bottle label and ordered phenobarbital 500 milligrams 4 times daily. The pharmacy label expressed the dose using apothecary measurements of 0.5 gr, which the resident thought meant 0.5 grams or 500 milligrams, instead of 0.5 grains, which would be 30 milligrams. The resident received phenobarbital 4 times daily for 3 days. After the patient suffered respiratory difficulties, the dose was withdrawn and the patient recovered. In a 2013 Maryland case, a 2-year-old boy's weight was entered into a database system as 35 kilograms, the equivalent of 77 pounds rather than his actual weight of 35 pounds. As a result of this error, the boy was prescribed a medication dose designed for a person twice his weight. The boy lost consciousness as a result of this dosage miscalculation, was fortunately readmitted back into the hospital in time, and was revived. Conversion errors are nothing new. Columbus even made conversion errors. He calculated the circumference of the earth in Roman miles instead of nautical miles, which led him to the Bahamas in 1492. Errors can occur when numbers have many zeros in them. Looking at these two examples, example 1 has 8 decimal places and example 2 has 7 decimal places. Numbers like this can easily be misread or miswritten. Scientific notation can help express numbers more clearly. Looking at these same numbers in scientific notation, you can see how much easier it is to identify and keep track of number values. A measurement can take on 2 categories, accuracy and precision. Accuracy is how close a measurement is to the actual or true value. Precision is how close measurements are to each other. A measurement can have good accuracy where the measurements are close to the actual true value and have a low level of precision where the values are not close to each other. Conversely, measurements can have good precision where the measurements are close to each other and have a low level of accuracy where they are not close to the actual true value. The goal is to have high accuracy and high precision. When values are not accurate and not precise, the measurement is not useful. Looking at this chart, we can summarize the categories. Science is continuously pushing the limits of measurements from the very small to the very large. Measurements as small as 1 femtosecond, 15 decimal places to the right, can be recorded, and measurements as large as 14 billion light years, 10 decimal places to the left, have been recorded. Scientific notation can help make these numbers more manageable. For femto units, we can write 1 times 10 to the negative 15th, eliminating the cumbersome process of writing 15 zeros that can easily lead to error. Likewise, we can write 1.4 times 10 to the 10th for 14 billion. To write scientific notation, we consider 3 components: a decimal part, an exponential part, and an exponent part. The decimal part brings a number to a single digit between 1 and 9. This makes the number easy to conceptually understand. The exponential has a base of 10, meaning it is multiplied or divided in increments of 10. The exponent, denoted as n, indicates how many times the base unit 10 is multiplied or divided to make up for the magnitude that was lost or gained when the decimal was moved. A negative exponent would indicate the decimal is being divided and the decimal moved to the right. A positive exponent would indicate the decimal is being multiplied and the decimal is moved to the left. Okay, looking at this number in scientific notation, we can see that the red part is the adjusted decimal part, the yellow part is the exponential part or base. These two words can be used interchangeably. Exponential and base mean the same thing. So if something is described in a base, it means the same as if something was described as an exponential. The black would then be the exponent, denoted as n. One of the important parts that I wanted to point out was there is a clear difference between the exponent, denoted as n, and the exponential. The exponential or base is in the yellow part, and the exponent is in the black part. So basically how this works is the base is the increments that it's multiplied or divided. The exponent would indicate how many times that operation is done. What we would have with a positive exponent would be 1 multiplied by 10, the base, or exponential, n times, n being the exponent. So 1 multiplied by 10 0 times would be 1. 1 multiplied by 10 one time would be 10, and 1 multiplied by 10 two times would be 100, and so on. Conversely, when we have a negative exponent, negative n, we would divide 1 by 10 n times. So 1 divided by 10 one time would be 1/10, and 1 divided by 10 two times would be 1/100th, and so on. Decimal literally translates from the medieval Latin word decimalis to uptenths. So when we plug a number into scientific notation, the number slides back and forth along the number line to give a single digit between 1 and 9. Looking at the number 249,784, we would slide the decimal to the left and between the 2 and 4 from its default position of the last number 4. This makes the magnitude 100,000 times less than what it was initially. So to bring it back to its original value, we need to multiply this number by 100,000. If we count how many times the decimal was moved from its initial location, we count 5 positions. We move the decimal to the left, so we would get a positive number, 5. We can then take this counted value and plug it into the exponent of the base, or exponential, which would bring the value back up to its original magnitude, because 10 to the 5th is 100,000. This results in a clear and compact expression. On the other hand, with very small numbers, we can slide the decimal from its assigned location to the right in the position behind the first whole number, in this case number 2, making the magnitude 1,000,000 times greater than its initial value. To bring the value back to its initial value, we need to divide this by 1,000,000. If we count how many times the decimal moved from its initial location, we count 6 positions. We move the decimal to the right, so we would get a negative value, or -6. We can take this counted value and plug it into the exponent of the base, or exponential, which would bring the value back down to the original magnitude, because 10 to the -6 equals 1 divided by 1,000,000. Again, this results in a clear and compact expression. A quick and dirty way of doing this is simply moving a decimal to get a single number. Count how many places a decimal moved and use that counted number as the exponent of the exponential. The decimal was moved to the left, so the exponent would be positive. Looking at this small number, we can move the decimal to get a single digit. Count how many places the decimal was moved and use that counted number as the exponent of the exponential. The decimal was moved to the right, so the exponent would be negative. To summarize this process, we have the following. Number 1, move the decimal to get a single digit. Number 2, multiply the arrived decimal number by base 10 and assign the exponent of the exponential the number of positions the decimal was moved. If the decimal moves to the right, the exponent is negative. If the number moves to the left, the exponent is positive.